Good morning. Welcome to the presentation of Boston House Price Prediction Machine Learning Project assignment for Skyfi Labs by me, Akansha Banerjee. First, the well-posed learning problem statement. Here the task P is to predict house prices based on features given as input. Performance measure P is minimizing errors of the predicted and the actual or observed prices. Training experience E is a database of actual house prices based on observed values of feature. Next, what were the choices made in designing the house price prediction learning problem as a flowchart? The overview of that. The type of training experience, database of house prices, determination. The target function, the features are real valued as well as the output. Representation of the learned function, linear function of 13 features. Determination of the learning algorithm, gradient descent, and finally the complete design of the problem. So, complete design of the problem. First, data acquisition. Next, data pre-processing. Third, EDA, feature selection and normalization. Next, train test split. After that, train the model, which includes hypothesis function selection, cost function selection, optimization algorithm selection. Next, after training comes visualization of the trained model as well as error visualization. Next, the model evaluation and prediction after reverting the normalization. First step, data acquisition. This data set was taken from StatLib library containing the house prices in Boston based on 13 features. And the 14th feature is the price of the house based on the values of the 13 features. These are the description about all the 13 features which were studied, and based on the values of these features, what was the price of the house. Next step was data pre-processing. It's always a good practice after data acquisition to see if there are any missing values in the data set. We count the number of missing values for each feature using the isNull function. A screenshot is accompanied with it. There are no missing values in this data set. Now, EDA step. In this section, we will use some visualization techniques to understand the relationship of the target variable or house prices with the other input features, which helps in the model selection. Using the describe function to get insights from the data, statistical insights. So from here we can observe that the target or the house prices data, the mean and median have similar values. The mean is 22.53, the unit is in thousands of dollars, and the median is 21.2. From here we can conclude the data set has symmetric distribution without outliers, and the range of prices is minimum is here we can see minimum is 5, unit is thousands of dollar, and maximum is 50 thousands of dollar, and the range of prices is 45, unit is thousands of dollars. Now, getting insights about outliers in each of the features using box plots. So we have plotted for each feature what are the box plot of the values. So based what we concluded is the features CRIM, ZN and B are having many outliers. Outliers are nothing but after the maximum value, these dots. Here we can see CRIM has lots of outliers. So either we ignore these features while training the model or use the min-max normalization. Now, finding the best parameter for training model, that is the best feature selection. For this we use correlation. Now, what is correlation? The extent to which is in magnitude and direction, to which change in one feature changes the other feature, and the change in magnitude and direction is mutual. Due to one there is change in the other feature, and due to change in other feature there will be change in the first feature as well. So why we are using correlation? What's the importance of it? To select the most important feature, change in which feature causes the most change in the house prices is used for making the linear regression model. Now for best feature selection, we have plotted a correlation of the target variable with the other attributes, and we see LSTAT or uh, lower status population in the area and number of rooms has high correlation values with the house prices. Now here there is a heat map of the house prices versus all the other features correlation values. The correlation coefficient ranges from -1 to 1. If the value is close to +1, it means that there is a strong positive correlation between the two variables. When it is close to -1, the variables have a strong negative correlation. From here we see LSTAT is highly negative correlated with the house price -0.74, and number of rooms is highly positively correlated with the house prices 0.7. So observation LSTAT or lower status of population in neighborhood, number of rooms in house or RM, PT ratio or parent teacher ratio in school in the area has the highest correlation with the target house price. LSTAT when increases, house price decreases. We saw it was highly negatively correlated, -0.7. RM when increases, house price increases, it was positively correlated, and PT ratio when increases, house price decreases. So from here, the choice of the best independent variable for training the model to predict house prices would be LSTAT. Now we are plotting a scatter plot to see how LSTAT and prices are varying with each other. So we see roughly the variation is looks like a linear variation. Now next step is normalization of the data. Why do we do it? Because it helps in faster convergence while finding optimal weights for the target function. As when all features are of same magnitude, the while converge finding the optimal weights during convergence, the uh, model would treat these both features having equal importance. If one feature is of higher magnitude than the other, it is treated more important than the other. While optimization, to avoid this, we do normalization of all features of data. So here consider a toy data set having two features to train, x1 and x2. X1's range is lower than x2. Here we have plotted there is a figure showing the original ranges of x1 and x2. The mean and the variance of both the features are different. Now what we do, first we make mean of both the data 0. Now, but we see the spread from mean for both the features is different. X2 has having higher variance as compared to X1. Now we made the data X1 and X2 having same mean and same spread. So types of normalization studied before making the choice for this project. Z-score, what is z-score and what it does to the data. For all features makes the mean 0 and the average spread of data from mean same for all the features. That means making the standard deviation 1. And second method is scaling. Scaling makes the range for all the features between 0 to 1. Now what did we use in our project is min max scaler, which use scaling or scaling all the features data between the values 0 and 1. Why? What was the reason for such a choice? Now min max normalization guarantees all features will have exact same scale but does not handle outliers well. Z-score normalization handle outliers but does not produce normalized data with the same exact scale. We saw during EDA, LSTAT did not have many outliers in the box plot. We saw that. LSTAT does not have many outliers over here. So we can choose min-max normalization for scaling for faster convergence. Now Now this is the formula that min-max normalization scalar use for normalization. It for every data point, it makes the minimum data point 0 and maximum data point 1, and or the range of the entire data set as 1. Now splitting the data into train and test set. Splitting the data into training and testing sets. Next we split the data into training and testing sets. We train the model with 80% of the samples and test with the remaining 20%. We do this to assess the model's performance on unseen data. To split the data, we use train test split function provided by scikit-learn library. We finally print the sizes of our training and test set to verify if splitting has occurred properly. Training and testing the model. A machine learning hypothesis is a next is the choice of the hypothesis function. A machine learning hypothesis is a candidate model that approximates a target function for mapping inputs to outputs, or which of the uh, formulas or which model, which mathematical model would accurately predict the relation between the input features and the output to produce the predicted values of prices. Now, what was the choice of our hypothesis function for this project? From EDA, we saw LSTAT was highly correlated with the target or the prices of a house, and both of them were roughly having a linear relationship from the scatter plot. So we will use equation of a straight line, that is h theta. The hypothesis function would be theta naught plus x theta 1. Our math model used over here is of that of linear regression. Now, what is cost or loss function, and which we have used for this project? It is a function that measures the performance of a machine learning model for the given data. Cost function quantifies the error between predicted values and the expected values, or the error between the actual values and what the model predicted, and presents it in the form of a single real number. Types of loss functions explored: mean square error, which is used for continuous data, and mean square error penalizes outliers. Uh, it penalizes outliers more than mean absolute error. Mean absolute error is also used for continuous data, and it ignores outliers effect on the while finding the optimal values of the parameters of the model. Cross entropy loss is usually used for classification problems. Now, cost function used in the project, would that be of mean square error? Now, why mean square error and not cross entropy loss? What does cross entropy loss formula mean, and why not cross entropy loss used for regression? Cross entropy loss penalizes even a single misclassification higher than the mean squared error, as classification model should be more sensitive to even a single misclassification. Or gradient of loss function is larger in cross entropy. And what does penalizing means? Changing the weights of model by some value. In regression problems, the data is continuous and the model works fine. For slight errors in predicted values, no need to penalize for small misprediction or change the parameter values. So next we will see the plot of mean square error and cross entropy loss for a classification problem of classifying data for ground truths y equals to 0 and y equals to 1. So here we can see how the gradient for a data point which has been predicted by the model belonging to the class 0.9, that means close to 1, whereas the ground truth was 0. So here we can see the upper graph is that of a mean squared error, and the lower one is for cross entropy loss. So for predicted value 0.9, we see the gradient for the cross entropy loss is much higher as compared to the mean squared error. But for regression problem, we don't need to penalize so much or change the gradient by such a large step. So we will use the mean squared error. optimization algorithm or gradient used for this project is gradient descent. So what is gradient descent? Iterative algorithm that is used to minimize a function by finding the optimal parameters or the parameters for which cost is minimum. What is needed to implement gradient descent algorithm? Cost function that needs to be minimized, number of iterations, learning rate to determine the step size at each iteration while moving towards the minimum, partial derivatives for weight and bias to update the parameters at each iteration, and the prediction function. So intuition of how gradient descent works. So let us make a simplifying assumption that the hypothesis function have only one parameter theta. That is, our hypothesis function is x into theta naught. So we have to find the optimal value of theta naught. So plot of predicted, that is h of theta on y axis versus actual y, is shown on the right side over here. Our aim is to minimize the average of the Scion distances. These Scion distances are the errors. These x's are the actual house price values, and on the line we can see the predicted house price value. Now the cost function becomes j of theta becomes the predicted house price value minus the actual house price value square by 2m. So we plot it on plotting the theta on x-axis theta versus the cost function or j of theta. What happens on training is, say we start from a point where the value of theta is at a. At theta at a we can see the cost is very large, or the error is very large for this value of theta. On reducing the mean square error, the theta keeps rolling down from A to minimum of B. At this value of theta, the cost function, the errors is minimum. But to make it reach the bottom efficiently, it should satisfy the two points. It should not overshoot the minima. That is, it at any iteration, the value of theta should not overshoot B. It should take a minimum number of steps to reach the point P. This can be achieved using optimization algorithm like gradient descent. So a better intuition of how gradient descent works. So what we have to answer is, what is the steepest way to descend in a parabola? So we have to find in which direction we should descend and by how much, what should be the step size at each iteration. Here alpha is the learning rate. Here we can see the formula for updation of the theta at each iteration. So here we are subtracting the directional derivative of the cost function at each iteration. So directional derivative, what it does is, it gives us the direction. So we should increase the value of theta and next iteration to reach B, or decrease the value. So in which direction we should move and how fast we should move, it gives that information. By subtracting, it gives the next value of theta near the optimal value B. Understanding how updation is happening, suppose case 1, the gradient is negative at point A. That means we are moving, increasing the value of theta to reach the point B, right? And how case 2, the gradient at point A is positive. Then what we are doing, we are decreasing the value in theta, minus positive, the value of theta is decreasing to reach the point P. So now next question, understanding what should be the step size in one iteration. We can see from the animation of over here, as we move near B, the magnitude of directional derivative is decreasing, or we are taking smaller step sizes at when as we reach the value of B, and at B the derivative is 0. So next is partial derivatives or gradients. Calculating the partial derivatives for weight and bias using the cost function. So this is the computational graph of how the partial derivative with respect to the weight is calculated. Now, results after implementation of gradient descent. So at each iteration, we can see the cost function is decreasing and we are changing the value of weight and bias. So finally, the optimal weight came out to be minus 0.75418 and optimal bias 0.6170. Now, visualization of results using matplotlib as animation tool. Matplotlib library of Python is a plotting tool used to plot graphs of functions or figures. It can also be used as animation tool. The plotted graphs when added with animations gives a more powerful visualization and helps the presenter to catch a larger number of audience. Using func animation class to visualize the animation of how the convergence of linear regression parameter happens. From matplotlib animation, import func animation class to use func animation class. Now this is the code for animation. Now this is the animation showing the red line is the hypothesis function, how it is turning till it reaches the optimal convergence value. The green are the scatter plot or actual test data, and the red line is the changing weight and bias value based on error on train data. Now error visualization. So this is the visualization of the error. The blue colored dots are the training data and the training data on the actual expected house prices, and the red line shows on the training data what is the predicted house prices. Yes, and we see are on plotting a graph between number of iterations and error. With each iteration, as the iteration increases, the error decreases exponentially. Now prediction of the house prices. Here we can see these are the predicted, the target Y value and the predicted Y value on the testing data. But the values are between 0 and 1. This is the visualization of the predicted values on the testing data. Yes. Now model evaluation, R square score. So what does R square score give information about? Assume we got R square score of 0.68. This means 68% of the data points lie on the target function or they are without any error. Or equation of the predicted regression equation, they are lying on that 68% of the data points, and remaining 32% of the data points don't lie on the predicted regression line or have errors in prediction. So code and result. So here we see the performance of the model using root mean square error score and R2 score of the training and the testing data. So what we see is the root mean square error score is 0.138. It's of low error value, and on the training set, the root mean square error is 0.13 and the R2 score is 0.53. That means 0.53% of the data points are lying on the hypothesis function or without any errors. And the model performance for testing set is the root mean square error is 0.138 or low 13% error, which is a good error, a low value of error, and R square score is 0.58 or 58% of the data points are predicted correctly using the hypothesis function. Now reverting the normalization from the predicted values, that is making the unit of the house prices from 0 to 1 to thousands of dollars. The predicted values are in the range of 0 to 1. This is not very useful to us when we want to obtain the price. We use the inverse transform function to scale the values back to the original representation. Thank you.